Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. So now we're going to move into looking at digital logic. And so we're going to talk about logic gates, and truth tables, and boolean expressions today in this video. And I want to introduce the three most basic gates that we'll look at, and that's the AND gate, the OR gate, and the inverter gate. When using just these three gates, designers typically call this AOI logic design or AND/OR inverter logic design. So we'll be looking at AOI logic design and introducing the gate and gate diagram, the truth table, and the logic expression. Let's get started. So AOI logic design. So there's three gates: AND gate, OR gate, and the inverter. And there are three structures that we're going to look at: truth table, gate diagram, and logic expression. So let's start with the AND gate. And we'll do the AND gate's truth table. Well, actually, let's write a definition here first. So the output is 1 if and only if all inputs are 1 for the system. All right, so what we're looking at here is a situation where our truth table is going to look something like this. We're going to deal with two input variables. I'm going to call those X and Y, and then we're going to have an output F. And so when we deal with all the combination with the truth table gives us all the combinations of inputs, all possible input combinations. There's a lot of little details that go into this. For instance, to make all the possible input combinations, you can count in binary starting from 0 as you go down the truth table. The second thing to note is that if you have n number of inputs, then the number of rows in your truth table is 2 to the n, 2 to the power of n. Because that makes sense, because for each input can be a 0 or a 1, so they basically double the possible number of input combinations. So if you have one input, you have 2 rows where the input is 0 or 1. If you have 2 inputs, then you have 2 to the 2, which is 4 rows, where one could be 0 or 1 for each case of the other being a 1 or a 0. So that gives you 4 combinations, and so on and so forth. So I don't want to go into all that detail right now, but we're going to go ahead and build our truth table. So we have 4 possible input combinations here for X and Y. And let me show you what I mean by counting up. So that's the binary number 0. This is the binary number 1. This is the binary number 2. And this is the binary number 3. And so we count up from 0 to 3. And this is going to be important when we look at some of the canonical forms, which we call min terms and max terms, as we go further into this unit. Okay, so what will the output function look like? So the AND is described as the output is 1 if and only if all inputs are 1. So where is that? That's when these two are 1 here. Both the X and Y inputs are 1, so the output's going to be a 1, and the rest of these are going to be 0. Sometimes I put a double line in between the inputs and outputs, or a thicker line, just so that we know what side is the input and what side is the output side. And so there you go. There's our truth table. So we have a truth table there. The next thing I want to look at is our gate diagram. And so an AND gate has a particular form. It has a straight edge, and then it has a rounded edge like that. It looks like a D, if you will. And then we draw the inputs as lines going into the straight edge, and then the outputs as a line coming out. And so then we can label our inputs X and Y entering the AND gate, and then the output F exiting the AND gate like so. So this is what an AND gate looks like. And so if ever you have an AND gate in your circuit, that's how you're going to draw it. And the last thing we have is our boolean expression. So there's a gate diagram, our truth table, and then our expression. And our expression is written as an equation, F equals. And so here we get to the AND operator. So the AND operator looks like the multiply operator from normal algebra. So it's a times. So F is X times Y. Oftentimes that's dropped and there's an implicit multiplication just by being next to each other. So that's usually the form that I would see as F is equal to XY. That's what we're looking at. So that's what we'll use. So in here, this is read as the output F is equal to X and Y. It's not X times Y because we don't have times here in Boolean algebra. We have logic operations like and or in inverter. Okay, let's look at the OR gate, the OR operation. So for the OR, a good definition would be that the output is 1. If, let's do this, if any of the inputs are 1. And so in the last one I said we're going to do with deal with 2 input gates. But you can have 3 input gates and 4 input gates and so on and so forth. So why don't we do a 3 input gate here just for fun. And so let's go ahead and do our truth table first. And so how many rows are we going to have if it's a 3 input gate? Well, that means we have 3 inputs coming in, 1 output. So Z can have 2 possibilities, so that's 2 rows. And then for each of those Z's, we can have 2 different Y's, so that's 2 times 2, that's 4 rows. And then for each of those combinations of Z and Y, we have 2 different X's, so we multiply by 2 again. So that's going to be 8 rows. And so we have 2 to the n rows, where n is the number of inputs. Okay, and so this probably needs to be a little bit longer. I don't want to run into my picture-in-picture. So let's do this, see if we can get all these in here. Okay, great. So here's a little shortcut in terms of building the truth table. We can count up here, 0, 0, 0, 0, 0, 1, and so on and so forth. But what we talk about is that Z here next to the output, that's the least significant digit. That's the least significant bit. And we get more significant as we move to the left. So X is the more significant bit inside this truth table. And so the least significant bit just alternates, it toggles each time. The next one is going to alternate by 2s. The next one's going to alternate by 4s, and then by 8s, and then by 16s, and so on and so forth. And your last, most significant digit is going to have half of the number 0, half the numbers are going to be 1. And so the answer here is, for the OR gate, is that the output is 1 if any of the inputs are 1. And so none of them are 1 here, but for every other case, there's at least one 1. So this is a 0 with a bunch of 1s. So we would say that this is very permissive, and so not very exclusive in a way. So the output of an OR gate is mostly going to be a 1. If anybody's a 1, it's going to be a 1. So any input's a 1. So it's very permitting in that way. Where an AND gate is very exclusive, very restricting. It only allows an output of 1 if all of the inputs are 1. So it's a way I kind of like to look at it there. So let's go ahead and draw the gate diagram for this. So in this case, for an OR gate, we have an edge here that's concave, and then we have curving lines that go to our output like that. And so you want to make sure, I think there's a couple things to make sure that you do is make sure that this is not a straight edge so we can distinguish it, and that this is not rounded like the D shape that we had for the AND gate. And if you do that, then most people will be able to recognize that as an OR gate. And then we have X, Y, and Z as our input variables and our output variable F. Writing the logic expression for this then is F is equal to, and we have X, Y, and Z, and the operator for OR looks like the addition symbol, the plus sign. And this is red. F is X or Y or Z. X or Y or Z. Okay. Lastly, we have the inverter. And the inverter returns the output that is opposite the input. Okay. An inverter is a one input, one output device. So let's go ahead and look at that truth table. So we have X and we have F. We have possibilities of 0 and 1 for X, and then we have output 1 and 0 for F. So this is really straightforward. The inverter looks like a triangle, and we'll have one input and one output like that, X and F. There's one thing that you have to put on the inverter, and this is a symbol that represents an inversion. You'll see it in other places as we kind of move along in here, and that's a circle. So this with a circle on the end, almost like a little, sideways Christmas tree, if you will, if you know that reference. And so that's what an inverter looks like. And that circle sometimes is used by itself to represent inversion, as you'll see if you dive in a little bit deeper. And then the Boolean expression is F is X, but how do we represent the operation? It's a over bar. So a bar over the X, and that is the operator that says invert or flip the bit for this one there, okay? Another thing you should know is that inverters are commonly referred to as NOT gates. So there's not. So F is not X. It's the opposite of X as you read that. Okay? Great. So those are our three basic AOI gates and their truth tables and their logic expression and their gate diagrams. So I hope you enjoyed. I hope you got something from that little lesson, and thanks for watching, and please come back for the next video as always. If you could like the videos and subscribe to my channel, that would be amazing as well, so we can be friends and hang out and that kind of thing. Yeah, just I would appreciate that. I appreciate you guys watching, appreciate everything that you're doing to be involved in this community of digital electronics. All right, have a great one.